So I wanted to review the fundamentals of special relativity, and to get started, let's think about what we mean by inertial reference frames. So the definition is that an inertial reference frame is one which is non-accelerating, and we also say that it is undergoing uniform motion. And this actually relates to Newton's first law, which you might recall says that an object in uniform motion will remain in uniform motion unless acted upon by unbalanced forces. Right, so what are some examples of inertial reference frames? So if we consider here on the left, we have got a train which is traveling at a constant velocity v to the right. And let's say we're just standing, our frame of reference is we're standing on the train platform. So from our view, it's traveling at this constant velocity, but we can change to the actual reference frame of the train itself. And so we're transforming from one inertial reference frame, namely the platform, to the inertial reference frame of the train. And both are inertial because the train is traveling at a constant velocity. But from the frame of reference of the train itself, it's actually stationary. And let's contrast this to a non-inertial reference frame. So if we consider a merry-go-rounder going around on a merry-go-round, we can see that their tangential velocity vt is constantly changing direction. It may be constant in magnitude, so they may have constant tangential speed, but the actual direction is changing, and that's caused by that centripetal force towards the center. And so since it's accelerating, it's not undergoing uniform motion. Newton's first law does not apply, but we know that if we transform to the reference frame of the merry-go-rounder, then under that reference frame, they're stationary. And by Newton's second law, for them to be stationary, we need that the net force is equal to zero. But if there's the centripetal force acting inwards, what's the other force which is acting outwards to counterbalance that one? Well, to do that, we introduce a fictitious force, namely what's called the centrifugal force. So what we can infer from this is that our measurements are only accurate, and so the laws of physics do not need to be adjusted to give accurate predictions in the case of transforming from one inertial reference frame to another inertial reference frame. But if we are transforming from or to a non-inertial reference frame, like in this case of the merry-go-rounder, we're transforming from the inertial reference frame of someone, a bystander, to the non-inertial reference frame of the merry-go-rounder, then we have to introduce these fictitious forces to get accurate predictions. And this relates to special relativity because, well, Einstein developed his two postulates. First one is that the laws of physics are the same in all inertial reference frames. So if we go from one inertial reference frame to another, the laws of physics are invariant. And this was called his principle of relativity. And this is what we expect from classical mechanics. He also introduced a much more counterintuitive postulate, though, and that is the speed of light in a vacuum is the same in all reference frames, independent of the state of motion of the body that emits the light. He called this his principle of light constancy. And this has a lot of unintuitive consequences when we take these two postulates combined. The first one we're going to talk about soon is called the relativity of simultaneity, which states that events which are separated in space, when viewed in one reference frame, might be simultaneous, but viewed in another inertial reference frame, we actually see them as non-simultaneous. There are other consequences as well, which we'll get into later, which is that we get these Lorentz transformations from one inertial reference frame to another, which tell us how to change our measurements from one frame to another. And from that, we can deduce length contraction and time dilation. All right, so for now, let's just double click on relativity of simultaneity. So imagine that we've got a train and we're just standing on the platform of a train station where we can see a train traveling towards the right with a constant velocity v. So we can see that it's undergoing uniform motion, and so we can change to the reference frame of the train if we so choose, and that'll be an inertial frame of reference. So imagine that a light strikes the center of the train, right, at a time t naught, and then it reflects off some object in the center, and then it propagates outwards, right? So from the reference frame of the train station or the train platform, we can see the light emanating outwards, and the train is slowly moving to the right. And then at a further later time t2, the left beam hits the back of the train. But because the train has moved to the right beam still hasn't hit the front of the train until a later time of t3, when it does hit the front of the train. So we can see that the speed of light in this reference frame is the same in both directions, left and the right, but because the train is moving to the right, it takes a longer time before the light hits the front of the train. Now what happens if we switch, like I said, we can to the reference frame of the train, which is also an inertial reference frame. We see that the same events of the light hitting the center of the train at, I'm going to call this t naught prime, the measurement from the frame of reference of the train, of that same event will lead to the light emanating in both directions. And because we stipulated that the light will be traveling at the same speed in both directions, have the speed of light c in the reference frame of the train, we should expect that it hit the center of the train, and so it's going to take exactly the same amount of time to hit the front and the back of the train. And so at a later time t2 prime, it'll hit the front and the back of it simultaneously. And so from the frame of reference of the train, these events occur simultaneously. So we can see that if we transform from one inertial reference frame to another, events that were viewed as dissimultaneous in one are actually viewed as simultaneous in the other. And this has a raft of consequences, which we'll get into later. Thanks for listening.